All right, welcome back. So, lab quiz tomorrow, as hopefully everybody knows. So important things about the lab quiz. Number one, don't come to lab. So the way that the lab quiz is going to work is that there will be 35 questions, and you'll have 30 minutes to answer them. And so it'll open up in Canvas at midnight tomorrow morning, I guess, and then it'll be open until 11:59 p.m. So just take it somewhere during the day tomorrow, or at some point during the day tomorrow. Whenever you open it, if you open it at 12:01 a.m., you'll have 30 minutes to finish it. If you open it at noon, you'll still have 30 minutes to finish it. So just whatever time works for you. And so that's what we're going to do instead of meeting in the lab tomorrow. So you're going to take the lab quiz. So don't come to lab tomorrow. Take the quiz instead. As far as the format of the quiz, so it's all multiple choice and identification questions. So for example, one of the questions you get might be a picture like this. And so it'll say, for the muscle pictured below, which of the following is an action of that muscle? Or for which of the following actions is this muscle an agonist? Okay, so what muscle is that? Anybody know? Infraspinatus, good. So it's an agonist for what action at the glenohumeral joint? External rotation. So the multiple choice answers then would be external rotation, internal rotation, protraction, upward rotation. I don't know. Pick 3 wrong answers. So then you'll just have to, so remember that if a muscle is an agonist for something, that's what it does. So when I say infraspinatus is an external rotator, it's an agonist for external rotation. So if it's an agonist for external rotation, what is it an antagonist for? Internal rotation. So that's the opposite motion, right? Good. So if it is an agonist for external, it's an antagonist for internal. So that's one type of question. Another type of question would be identify the infraspinatus muscle. So then rather than it being highlighted like it is, I would have drawn a box that you can't see, and I actually have to go through, it's super tedious, with the mouse and like click all these points. But basically, so what you'll have to do, it would just be, again, this picture without the highlight and say identify the infraspinatus on the model's right side. And so all you got to do is click somewhere in the middle of the belly of that muscle. So on any of those identification questions, try to click as close to the middle of the structure as possible. So if I ask you about something like the acromion, click right dead center of the acromion. Don't click like over in here, because then you may or may not be on it, okay? So make sure you click in the middle. And then the other types of things you might see would be a picture like this. And it'll say this is a posterior view of the scapula. Identify the acromion. Identify the origin of the infraspinatus muscle. So if it's a question like identify the origin of, same kind of thing. So the infraspinatus muscle originates all in here in the infraspinous fossa. So then just click somewhere in the middle of the infraspinous fossa. Like I said, so 35 questions, 30 minutes. I try to make you work a little bit quickly so that you can't look everything up, because nature of the test or the quiz there, that people have the opportunity to look some things up. So I'm trying to make you work fairly quickly so you can't look absolutely everything up. I would say because it's something that you take at home, don't let that lull you into a sense of complacency on studying. Oftentimes students are like, I'll just take it at the house so I can look stuff up as I go. And then that tends to go poorly. So just make sure you look at it before you actually open the quiz. Questions or anything about the format or anything else? Nope, awesome. I'm going to send out an email after class that'll say the same kind of stuff. Don't come to lab and all of that stuff. So cool. All right, so that's the quiz. So like I said, do that tomorrow. And so we'll pick up, so I did 2 videos Friday and Monday on the muscular system. So Friday, talked about basic muscle structure, talked about the layers of connective tissue, epi, peri, endomysium, all of that stuff. And then last time, talked about the process of muscle contraction. So that's pretty complicated. So if you haven't watched that, make sure that you go back and do that, because those are things I like to ask questions about, are kind of the sequence of muscle contraction. That's important to understand. All right, so where we left off was talking about motor units. So what is a motor unit? Well, you're looking at 2 of them. So a motor unit is an alpha motor neuron and all of the muscle fibers that it innervates. So the wording is a little bit different on the slide. So muscle fibers that it supplies is the same thing as muscle fibers that it innervates. So we're going to talk about 2 types of motor neurons. One thing to understand is a motor neuron is a nerve cell that causes muscles to contract. So motor neuron is a nerve cell that activates muscles. So alpha motor neurons activate voluntary skeletal muscle cells, because you've got another type of muscle cell inside of all of your skeletal muscles called muscle spindles, and they're going to have their own separate set of motor neurons, and we'll talk about them later. So a motor unit then, an alpha motor neuron, and all of the muscle fibers that it innervates. So motor units vary in size. Some motor units are really small. So for example, the two motor units you've got here, so what you're looking at, and they're labeled, but just to emphasize, what you're looking at here, so obviously this is the spinal cord in the middle. And so the spinal cord, again, is that bundle of nerves that brings signals away from the brain, causing muscle contraction, or brings information back to the brain about your environment. It's hot in here, it's bright, those kinds of things. I'm moving, I'm not, that kind of information. So in the, I mentioned this last time, but in the ventral horn of the spinal cord, so that's where the cell bodies of those alpha motor neurons sit. So these little dots are their cell bodies. And then they have a long axon, think of it as an electrical cable, that goes out to muscle fibers. And so this purple one is an alpha motor neuron that innervates, or that activates, 2 skeletal muscle cells. So its motor unit size is 2, right? As opposed to the red one, its little cell body is here, and it's going to interact with 1, 2, 3 skeletal muscle cells. So those are 2 differently sized motor units. The red one is larger because that alpha motor neuron activates more muscle fibers. So a small motor unit may be as few as 4 muscle fibers. A large motor unit may be as many as a couple thousand. So it depends in part on what the job of the muscle is. So for example, you got some little muscles that move your eyes. We need really small movements of your eyeballs to be able to track things and to be able to focus. And so those motor units in the eyes are really, really small. So each individual motor neuron may innervate only 4 muscle cells. As opposed to in your gastrocnemius, the superficial calf muscle, those motor units may be thousands of muscle fibers. Because I don't need really fine control in my calf, I need to be able to push off really hard, right? And so because I need big, powerful contractions, we want to activate lots of muscle cells. So in a muscle that produces really big, powerful movements, you have big motor units in general. And then in muscles that do fine motor control, you tend to have lots of smaller motor units and fewer muscle cells, obviously. All right, so the concept of muscle twitch. So every time that alpha motor neuron depolarizes, every time it sends its electrical signal, it'll release acetylcholine at the neuromuscular junction, and this is the stuff I talked about last time. Acetylcholine causes the muscle cell to depolarize, causes the release of calcium, and you get a very brief interaction of myosin and actin, and then the calcium goes away, gets pumped back into the sarcoplasmic reticulum, and actin and myosin stop interacting. So muscle twitches that really quick. It contracts and it stops. Okay? So an important thing to understand about motor units is that if an alpha motor neuron depolarizes, if it sends an electrical signal, all of the muscle fibers that it is attached to or interacts with will contract or will twitch. So that's the all or nothing principle. So if that alpha motor neuron depolarizes, all of the muscle cells that it interacts with or that it innervates will contract. So if I activate that purple motor neuron, those 2 muscle fibers that it interacts with will contract. But the rest of them will stay at rest, right? Because they're not activated by that purple one. If I activate that red motor neuron, those 3 muscle fibers will contract, okay? So what I'm getting at there is something that's back on this slide called the size principle. So if we want a really big, strong muscle contraction, we have to recruit more motor units. And we actually start with the smallest motor units first and then work our way up to the larger ones. So another thing to be aware of is a single alpha motor neuron is hooked up to one cell type or one muscle fiber type. So an alpha motor neuron is either attached to all type 1 fibers or all type 2As or all type 2Xs. So if I'm engaged in a really low intensity muscle contraction, so for example, let's say I want to pick up this remote control that's up here, right? I'm going to use biceps to do that because biceps is the primary flexor at the humeral ulnar joint. And so, but this thing only weighs a few ounces, so it's not going to take a lot of muscle contraction to do that. I don't have to generate very much tension in the biceps. So I can get by with some of the smaller motor units. I can activate only my slow twitch small fibers, and I can pick this thing up. But if instead of picking up something that weighs only a few ounces, I had, a 40-pound dumbbell, that's going to take some real tension generated by the biceps in order to lift that weight. And so what we'll have to do then is the type 1 fibers by themselves aren't strong enough. So now I'm going to have to get some help. And so I'm going to start out by recruiting, there's my little arrow, start out by recruiting the type 1 fibers down here. If that's not enough to move the weight, then I'll recruit the type 2A fibers, those intermediate fibers. And if that's still not enough, then I'll recruit the type 2X fibers, the largest of the muscle fibers. So the size principle is that we recruit motor units, but also muscle fiber types in order from smallest to largest. So we start with your type 1 fibers. If we need a stronger muscle contraction, we work up to 2As, stronger muscle contraction, 2Xs. So an example like I give of that sometimes is if you're helping a friend move, they're moving apartments or something like that, and they're like, hey, go pick up that box over there. It's a box full of pillows. And you're like, oh, okay. And you go to lift it up. So you're assuming then that's going to be lightweight. You don't really have to generate very much tension. But it turns out it's a box full of textbooks, right? So if you go and apply the force you thought you were going to have to apply for pillows, that thing's not going to move. So you recruited initially your type 1 fibers. It's not enough. And then you have to work your way up. All right. Other things on there, synchronous versus asynchronous firing. So synchronous means at the same time. Asynchronous means not at the same time. So we see synchronous firing during really, in a sporting context, during really powerful movements or during movements where we need to generate a lot of muscle tension. So if you're going to go max out on deadlift, for example, you need to recruit all of your motor units at one time. So you're going to have synchronous firing. So going back to here, rather than recruiting the purple and then the red, if I know that that's a really heavy weight and it's going to take a lot of muscle tension to lift it, I'm going to try to recruit both the red and the purple at the exact same time. Try to get them sending as many signals as I can as quickly as possible. So that's synchronous firing, recruiting all the motor units at one time. So again, we're going to do that during really powerful activities. So vertical jump, sprinting, lifting heavy weights, those kinds of things. Asynchronous firing we see during lower intensity activities. So if you're doing something like running a 10K, so you're running 6 miles. So if you're doing that, you're going to run at, 8-minute mile pace. So to run at 8-minute mile pace, you're not going to push off quite as hard. Your stride length will be shorter with each step as compared to a sprint. If you're sprinting, you're going to push off the ground really hard. You're going to have really long strides. So in those endurance types of runs then, you're applying less force, so you're not pushing off quite as hard. You got shorter strides. So because of that, I don't need quite as strong of a muscle contraction. And so what we'll do is we'll recruit only, let's say, 1/3 of the hamstring muscle fibers on the first stride. And then the second time that leg hits the ground, I'll recruit the second third of the muscle fibers that were at rest on the first stride. And then on the third stride, I'll recruit the last third. So that's asynchronous firing. I'll activate part of the muscle or part of those motor units for one stride or one action, and then pick up another group the next time, and then another group the next time, and then we start back over. So the reason that we do that is to conserve energy. Well, 2 reasons. 1, we don't need all those motor units, but 2 is to conserve energy. So during endurance type training, then we get better at resting motor units some of the time and then activating them later. So that's actually kind of a learned skill. And so is synchronous firing. So as we'll talk about again probably on Friday, one of the important adaptations to strength training, so if you take somebody in and have them lift weights that's never lifted before, for the first 2 to 4 weeks of training, they're not really going to get a whole lot bigger, right? You're not going to notice really obvious muscle hypertrophy or muscle growth, but they're still going to get stronger. So how did they get stronger if their muscles haven't appreciably changed? Because you also don't see the metabolic changes inside the muscle for about 4 weeks. So how'd they get stronger? Well, the answer is the nervous system. The brain got better at recruiting those motor units that it needed and recruiting them all at the same time. It gets better at synchronous firing. And so if you do things like vertical jump and you practice the vertical jump and practice really explosive movements, the brain gets better at them. It's a learning effect, right? So it gets better at synchronous firing. Same kind of a thing if I'm an endurance athlete, taking one step and recruiting part of my motor units one time, letting them rest, etc. You get better at doing that too. Where that can become problematic, of course, is that the body is really good at adapting to different stimuli. So the body adapts in one way to strength and power training. So if you're lifting really heavy weights or sprinting, there's a certain set of adaptations that accompany that, and there's a different set of adaptations that accompany endurance training. So where some of this stuff matters on a practical level is, for example, at a previous institution, athletes like to ask me about their training programs, which I hated, because like it's always nice to help, but at the same time you hate to question what the coach is doing. But at that time, the volleyball team for that school was getting ready to run a half marathon, right? So they're going to run 13.1 miles. Does that make sense for volleyball players to train that way? Of course not, right? During the course of a volleyball match, is there some aerobic component during the recovery phase? Sure. But volleyball athletes are power athletes. They are sprint athletes. They got to get from A to B, and they got to jump real high. And if they then spend several months running 10 miles, 13 miles, etc., then what they're going to do is actually train their muscles to work the other way. They had been training themselves for synchronous firing to maximize the vertical jump, and if they go do a bunch of endurance running, they're actually training their nervous system to act this other way. And so it'll probably decrease their vertical jump. There are other reasons that they're not going to be able to jump as high after that training, but this kind of confusion of the nervous system is one. So that motor unit recruitment then is pretty important. All right, well, what if I've recruited all of my motor units and I still can't lift that weight? Well, we have one other way to increase muscle tension, and that is called rate coding. And so what rate coding means is the number of times per second that the alpha motor neuron depolarizes. So rate coding, the number of times per second that the alpha motor neuron depolarizes. So viewed another way, that is how many signals, what is the frequency of stimulation, how many electrical signals is that alpha motor neuron sending per second? The higher the number of signals, the greater the frequency, the stronger muscle contraction you're going to get. So for example, and I'll go through here real quick. So if we just get one signal, so the alpha motor neuron depolarizes one time, causes a quick release of calcium, get interaction of actin and myosin, but that calcium has moved back into the sarcoplasmic reticulum pretty quickly, then the muscle drops back into relaxation fairly quickly. But if I send 4 signals in quick succession, then we pump some of the calcium back into the sarcoplasmic reticulum, but not all of it. So that calcium that stays out allows for some continued interaction of actin and myosin. If we get another electrical signal, we're going to release more calcium, and then we'll pump it back in, but we get another electrical signal, we'll release more. And so because of that, the more electrical signals you get per second, the longer you sustain that release of calcium from the sarcoplasmic reticulum, the longer you keep those active sites on actin exposed, and so myosin is going to keep interacting with those sites until we max out at somewhere around 80 pulses per second. So effectively what happens from a rate coding standpoint is if I don't need a very strong muscle contraction, that motor neuron may send 20 signals per second. But if I need, if I'm maxing out, if I'm lifting the heaviest weight possible, then I need lots of impulses per second. And so then we'll get a frequency of 80 pulses per second as opposed to 20. So you can send, the alpha motor neuron can depolarize with greater frequency. Again, it can depolarize more times per second, allowing calcium to stay out of the sarcoplasmic reticulum, allowing continued interaction of actin and myosin. So the takeaway there is we'll use muscles like biceps for elbow flexion all the time. It's always an elbow flexor, right? But there are times I don't have to lift very much weight, or there are times when I do have to lift a lot of weight. And so how do we use that same muscle? How do we grade or change the amount of tension that's produced? There's 2 ways that that's done: motor unit recruitment and then rate coding. All right, and let's apply that even a little bit more. It's kind of an odd drawing, but I'll explain what it means here in a second. All right, so what this is kind of that same schematic I was just describing to you. So at the bottom there it says percent of aerobic capacity, or VO2 max. So your aerobic capacity, you'll talk a lot about in exercise physiology, but your aerobic capacity is your ability to make ATP using oxygen. So you can work at a higher intensity. You can work above your aerobic capacity, which is why it goes above 100%. So 100% again is just your maximal ability to produce ATP using oxygen. So one of the ways to think about that is when you're working at 100% of your aerobic capacity, that's about your fastest mile time. So about the fastest pace you can run a mile. Let's say you're going to run a 6-minute mile. That's about as fast as you can deliver oxygen to the tissues and remake ATP using oxygen. But can you run faster than whatever your maximal mile time is for a short distance? Well, of course you can, right? You can sprint, right? So you run a lot faster for an 800 than you would for a mile, run a lot faster for a 100 than you would for an 800, right? So you can sprint. And so if you're sprinting now, you are operating above your aerobic capacity. You are using ATP faster than it can be remade with oxygen. So what you have to do then is remake that ATP anaerobically. So you have to break down glucose, glycogen, not in the presence of oxygen. So the byproduct there is lactate or lactic acid. I mentioned this last time. Or you have to use the ATP phosphocreatine system, which again, you have limited stores there and you deplete that system after about 10 seconds. So we can work above our aerobic capacity, like sprinting, we just can't do it for very long. All right, so we're going to ignore that above the aerobic capacity for now. So we're going to say we have an athlete who runs a 6-minute mile. So their aerobic capacity is somewhere around that pace. So if that athlete then, because they max out at a 6-minute mile, so here at 75% of their aerobic capacity, they're running about a 7:30 mile. Or here at 50% of their aerobic capacity, they're running about a 9-minute mile. So if this athlete goes out and either just does a light walk, so they're walking from class to class, they're over here, kind of on the lowest end of their aerobic capacity range. So the muscle fibers that they're recruiting for that task are their type 1 fibers. Okay, so they're only going to have to use slow twitch fibers. As they move from a walk to kind of a jog, now they're still over here in the slow twitch fibers. Now they're going to be at like a slow run, again, 9-minute mile pace or less. They're using all type 1 fibers. Now when they transition and they start running, so faster than 9-minute miles, but slower than 7.5, so kind of in that 8-minute range, now they're using type 1 and type 2As. And anytime they're running faster than a 7:30 mile during their training, they're going to also be incorporating their type 2X. Well, why does that matter? The reason it matters is, again, that muscle cells adapt to training stimuli. So to endurance training stimuli, muscle cells will add capillaries, they'll add mitochondria, they'll add the enzymes in the mitochondria that help you use oxygen to remake ATP. We start to get into some of the asynchronous firing. So the muscle cells get more aerobic in response to endurance type training. They get better at using oxygen. Now they're not quite as good at producing lots of force anymore, but they're really good at using oxygen to remake ATP. So if that athlete, and you see this often in recreational runners, so if somebody says, oh, I'm going to go run a 10K. Normally, if they don't really look into it, the way that people train is they'll go out and like run a mile today and run 2 miles tomorrow and then work their way up to 6 miles and then they'll go out and run the race. But of course, during the race, you're going to run faster than you do during training because you don't want to let that guy beat you. Like, that guy doesn't look very fast. What's he doing in front of me? Right? And so you run harder than you're accustomed to running during training. Well, what happens then is if people self-select a pace, if you just go out and run a mile, typically people are going to run kind of in this range, maybe a little bit slower, more like over here. Okay? So they only get those training adaptations. They only get more mitochondria, more capillaries, et cetera, in those type 1 and type 2A fibers. Their type 2X fibers are basically entirely untrained. And then they go out there on race day and they're like, oh, I can't let that guy beat me. And so now they're running kind of over here. They're having to use their type 2X fibers, but because they never ran at that pace in training, they never trained those fibers. Those fibers don't have more mitochondria than they did before. They don't have more capillaries. They're not as oxidative as they could be, right? So you have to recruit those fibers in order to cause them to make those adaptations. Very similar kind of schematic if we talk about strength training. So we're going to ignore, again, above 100%. So we'll pretend here 100% is your 1 rep max, 75% somewhere around your 6 rep max, and this is probably more like your 12 rep max. Okay? So if I go to the weight room all the time and I'm lifting and I'm doing sets of 12, then all I'm using, or almost all I'm using, are type 1 fibers. So those type 1 fibers are going to adapt to that training. They're going to add more actin, more myosin. They're going to get bigger. But if I don't train with heavier weight than that, if I always train at 12s and 15s, well, then I never engage these type 2A fibers, right? And so they're never going to grow. So in order to engage these fibers, I have to lift somewhere between 6 and 8 reps. give or take. The areas are approximations. But basically, once you start lifting heavier, so once you get more like 6 rep max, now we're including both the type 1s and the type 2As. And then once you drop below, so now when you're 5 reps and lower, now you're getting at the type 2Xs as well. And so the idea there is if you want those biggest fibers to grow, the type 2Xs, you got to train them. And so you have to lift heavy weights to be able to recruit them. So you got your 5 rep max or lower, or more weight. So you got to lift heavy weights to stimulate those fibers to cause them to grow. So one of the most basic training schemes is called linear periodization. And I'll be teaching an entire class on training protocols next summer for those of you that aren't super bored right now. So look for that online. But the linear periodization, the basic way it works is you start with, let's say the lift you want to train is squats. So this week on squats, I'm going to do 3 sets of 12 at 100 pounds. And so I can do that for as many as 4 weeks. After about 4 weeks, you've maximized the adaptations to that training stimulus. Certainly you can change it sooner, like I usually change every 1 to 2 weeks. But certainly you don't want to do it more than, you don't want to do the same weight or same workout for more than 4 weeks. So you do your sets of 12 for 2 weeks. 2 weeks later, you do sets of 10. 2 weeks later, you do sets of 8, and then you just kind of work your way down. And so what you're doing then is you're working your way through training the type 1 fibers first, and then as I get heavier, I start to get into the type 2As, and then at the end of the program, when I'm lifting sets of 5, now I'm training the 2Xs. So we're causing all of those muscle fibers to get larger and to get stronger. So that's kind of the idea behind a really basic training program. Any questions about any of that stuff? Your really elite power and sprint athletes do both of these things at the same time. So if you've got somebody that is, let's say, an Olympic weightlifter, and they're trying to lift 500 pounds overhead, or let's go with they're trying to clean 500 pounds. When they do that, they are going to be, because of their training, they're going to be really good at synchronous firing. They'll recruit all of the relevant motor units at one time, and they'll maximize rate coding basically instantaneously. So they'll send 80 pulses per second and recruit all the motor units at one time. And so again, the size of the muscle is obviously tremendously important, but just as important, or almost as important, is activating those fibers, right? And so we have to be able to do, if we want to maximize performance, certainly in a sprint event, we've got to be able to do both of those two things at the same time. All right, so we talked about those. All right, so let's talk about muscle contractions. So isotonic contractions, isotonic means same tension, and it's kind of a misnomer in that, like traditional weightlifting, squat, bench press, deadlift, is referred to as isotonic training. Because the thought is that if I'm, let's say, squatting 100 pounds, that the 100 pounds at the top weighs the same at the top as it does at the bottom, so the muscle tension throughout the range of motion should be the same, and so it is isotonic, it's equal tension. Of course, that's not how it works in real life, right? The muscle exerts more or less tension depending upon moment arms and other factors. So, like I said, it's kind of a misnomer, but isotonic contractions mean same tension. And so in textbooks, when you're looking at isotonic stuff, they're talking about like what we would consider traditional weightlifting. So barbells, dumbbells, those kinds of things, kettlebells, etc. So isotonic contractions, there's 2 types of them, concentric and eccentric. So in the case of a concentric contraction, the muscle is shortening and moving the load. So whatever external load you're trying to lift, the muscle is overcoming that resistance and the muscle is shortening. So one of the other things I want you to know about concentric contractions is they are acceleration, speeding up contractions. So if we think about something like a bicep curl, it's a pretty straightforward exercise. You start with a barbell in front of your thighs, you lift it up right in front of your face or close to your face, near your chin. So the up phase of that is the concentric phase for the biceps. The muscle is contracting and shortening, right? So that's all pretty straightforward. From an acceleration standpoint, if we think about something like a throwing motion, when somebody goes from full external rotation of the shoulder and abduction, when they start to actually get into their pitch and move their arm into internal rotation and adduction, that's going to be a concentric action for pec major, lats, teres major, subscap, etc. So they're going to be contracting and shortening to accelerate the arm to throw the ball. So concentric contractions, muscles contracting and shortening. and also we see those during acceleration, speeding up. Eccentric contractions are the opposite. The muscle's contracting but lengthening. So going back to the bicep curl, that's the down phase. So when you fight the weight on the way down, where the muscle's contracting but it's still getting longer, that's an eccentric contraction. So eccentric contractions not only rely on the contractile component of the muscle, the actin and myosin, but they also, as the muscle is being forcibly stretched, they also stretch out that connective tissue. So they stretch out the cell's membrane a little bit, which is not part of the connective tissue, but they do stretch out the cell's membrane. They stretch out the basal lamina. They stretch out the endomysium. And so eccentric contractions then tend to damage those connective tissue structures. They tend to damage the endomysium. Well, why does that matter? Well, muscle growth is the product of repeated damage. So eccentric contractions do more damage to the muscle, so they're actually going to be very important for causing the muscle to grow larger and stronger. So sometimes you see, like, so for example, my son's 10, and so I'm trying to get him to lift weights, kind of, which is, man, teaching a 10-year-old to squat is difficult. We're doing like front squats with a dumbbell at this point. But one of the things that's the hardest for him is engaging the eccentric contractions. Like he'll do a lift and he'll just like relax, like just noodle arms, just drop the weight. It's like, don't do that. You gotta like fight it on the way down, or half-assed fight it. But the reason that's important again is because in fighting through it, now we're gonna damage the muscle. We're gonna cause soreness by doing that, but then that's an important stimulus for muscle growth, and so that's gonna help you adapt. So, you know, if you see somebody in the weight room do the whole like lat pulls, pull it down, and then just like relax, don't do that. You want to fight it, okay? But know that that's going to make you more sore. So that's kind of the trade-off there. So we can do exercise programs that emphasize eccentrics, but they're going to cause lots of soreness. So for example, there's, I don't know if any of you have ever heard of it. There's a gym chain called Curves. Anybody ever heard of that gym chain? No. There's a few of them up here. I had to look it up last semester. They're mostly in Texas, or at least my experience with them is mostly in Texas. There's a lot of them, but there's not very many up here. But the gist of it is, they have all hydraulic machines. It's a gym that caters exclusively to women. I don't think men can sign up. But it's kind of like a circuit. If any of you are familiar with Planet Fitness, where they have the little circuit area. Yeah, I got a Planet Fitness membership. I'm not proud of it. So, but they have the little circuit area. And so Curves is the same kind of thing, but rather than having like machines that are plate loaded, they have hydraulic machines. And so basically what will happen is if you're doing, let's say, hip adduction, so bringing your legs together, or hip abduction, bringing them apart, it'll be the same machine. So the machine fights you on the way in, so you bring your legs together, and then you push them back out. It doesn't actually pull them back out. So there's no eccentric phase. It's all concentric training. So the good thing about that is you don't get as sore, right? If you never do an eccentric phase to the movement, you don't get as sore. And so that gym has chosen those types of machines deliberately because they don't really want to make their clientele sore, because when people get sore, they don't come back, right? Because you go get sore from your exercise program, you're like, man, that sucked. I can't really walk for a couple days. I'm not going to go back and do that again. And so they're trying not to make their clients sore with the hope of improving retention. So it's an interesting way of doing that. So if you minimize the eccentric contractions, you tend to minimize soreness. Isometric contractions. So in an isometric contraction, there is no change in muscle length. So usually you are kind of fighting against an immovable object. And so you're contracting the muscle as hard as you can, but you get no change in length and no change in joint angle. So we see isometric contractions. You can do them intentionally, like powerlifters do them as part of their program. So one of the things, if you've ever done bench press, you know you get stuck kind of in that mid-range during the pressing motion, the changeover from pecs to triceps. And so one of the things that powerlifters will do sometimes to train that, to get through that sticking point, is basically they'll get under a power rack and they'll push the bar into that part of the range of motion and just push as hard as they can for 6 seconds. And so that's an isometric contraction, no change in muscle length there, trying to increase strength at that joint angle. We also see isometric contractions as stabilizing contractions. So like right now, as I'm kind of walking around a little bit, I'm getting isometric contractions throughout my spinal column, stabilizing my spine. And you get them, we've talked about, the scapular muscles, obviously. So when I'm moving my arm, or I'm kind of up here, I'm getting some isometric contractions in my scapular muscles trying to stabilize it. So isometric contractions, in a more activities of daily living sense, are stabilizing contractions. So fun story about isometric contractions, because I like telling stories about history. Anybody ever seen a rack like that? It's called an isometric rack. Connor has. Where'd you see that? Okay, that's an old rack. So the isometric racks, what happens there, so this guy's doing, he's training the snatch, so he's training to lift the bar directly overhead. And so you can see there's two sets of pins. There's one here that he's pulling against right now, and there's one here below that. And so basically what you would do is you'd rest, okay, and then you pull the bar up against that again for about 6 seconds, sometimes as long as 10. Just pull as hard as you can, pull as hard as you can, relax, and then you do that for several sets, all right? So isometric training was all the rage in the US in the early 1960s because there were 3 weightlifters who were part of the York Barbell Club and therefore part of the US Olympic weightlifting team who had made just incredible gains starting about 1959 and into 1961. They'd put, I forget the percentages, but just mind-blowing improvement in their snatch, their clean and jerk, and their press. And so the coach of the Olympic weightlifting team was a guy named Bob Hoffman who owned a magazine called Strength and Health. And so in that magazine, he wrote an article that he titled The Most Important Article I Ever Wrote. And so he talked about the improvements that those athletes had made. He said, well, the reason they've been making these improvements is because they've been doing these new isometric contractions that we've learned about. And so our company, York Barbell, is going to sell these isometric racks, and so you should buy them, and they're going to really improve your training. And the lifters across the country started doing isometric training. The Green Bay Packers did isometric training. Vince Lombardi, not a fan of barbell training. He thought it would make athletes muscle-bound, but he was okay with isometric training. So the Packers had these isometric racks like that, where they'd walk out before practice and they do like partial deadlifts and pushes and whatever else, and then they go to practice. Couldn't lift weights, but we could do those. So the question I have for you, though, is given that time frame, again between 1959 and 1961, what else might have explained those lifters' tremendous gains, because nobody else really got all that much stronger using isometric contractions? Anybody got an idea? Anabolic steroids, the first steroid in the US, Dianabol, invented in 1958. And so those athletes were all taking little pink pills, aka Dianabol, and using isometric training. So they got super strong because of the anabolic steroids, but they also did that. And so the article that spurred this movement talked all about the isometric training, didn't mention the drugs at all. So anyway, so like the research on strength training in the 60s is all like isometrics. Like, how do we get those results? Why is that not happening for us? All right, concept of overload. So now we're talking a little bit of training theory for a second here. So one of the amazing things about the body is how adaptable it is. So if you expose the body to a stimulus beyond that to which it's normally used to, probably a better way of phrasing that, but if you expose the body to a stimulus it's not used to, the body is pretty good at adapting, right? So bones can adapt, bones can remodel, they can get thicker in response to different training stimuli. Muscles can obviously get larger and get stronger and all of that. But in order for that to happen, you have to make them work harder than they're used to working. And so that's the concept of overload. So you can invoke overload in a number of different ways. One of the ways is you can increase intensity. So in the case of strength training, increased intensity is just lifting more weight. So as you drop from sets of 10s to 8s, you add weight to that, right? So your overload now is that you have increased the intensity by increasing the weight. Increased volume, in the case of strength training, is more repetitions. So you either add sets or you add reps. So last week I lifted 100 pounds 10 times. This week I lifted 100 pounds 12 times. So I've increased the volume. The intensity is the same, but the volume is going up. And then frequency is how often it happens. So you lift more times per week. That would be increased frequency. So by manipulating those different training variables then, we can invoke an overload stimulus, or induce, is a better word, induce an overload stimulus to cause the muscles to adapt, to cause them to grow in size and to get stronger. So ideally that program is planned. And there's a fun story about overload too. So the supposed originator of the concept of progressive overload, where you change something in the training program to continuously invoke overload, the supposed originator of that program, or that idea, was a Greek wrestler in the 6th century BC. His name is Milo of Crotona. And so the ancient Greek Olympics were a religious festival, right? So there were, there's a 200-yard sprint, there's, depending upon which year span you're talking about, there's wrestling, and there's a number of other events. but they're held at the temple of, or in front of, the temple of Zeus, right? So it's overarchingly a religious festival. And so what Milo did, supposedly, again, this is a legend, but supposedly what Milo did was to train for the Olympics. After one Olympiad was over, he went back home to Crotona, which is in southern Italy, and he grabbed a newborn ox calf and he threw it on his shoulders, and he would just walk around with this ox calf, all right? So tomorrow, that ox calf's going to be a little bit bigger, so it's going to weigh a little more. So throw it on his shoulders, walk around with it again. And now here's where it gets into, like, some of that might be true, but here's where it becomes legend, is that supposedly he would do that for 4 years. Now, obviously, at the end of 4 years, you're not throwing an ox calf over your shoulders. That thing's too big. But supposedly, he'd throw it over his shoulders, right? And then the best part of the legend is he would take it with him to Olympia, because Olympia is only every 4 years, like the modern Olympics are. So he trained with this thing for 4 years, takes it to Olympia. He would throw it on his shoulders, carry it the length of the Olympic Stadium, which is about 200 yards, and then he would sacrifice it, and then he would, because again, it's a religious festival, he'd leave the bones and the fat for Zeus, which is conveniently what Zeus liked the most, and then he would eat the meat as his pregame meal. And so Milo won 6 consecutive titles in Olympic wrestling, right? So 24 years he was undefeated in wrestling at the Olympics. And thinking about the lifespans in the 6th century BC, that's incredible. So he was doing something. He was doing some kind of strength training, and he was probably lifting an ox calf or something like that to train. But so that's where the idea of progressive training comes from, is from this ancient Greek Olympian who would supposedly carry around an ox calf. So not coincidentally, the first barbell company in the U.S. was named the Milo Barbell Company, because it's named for this Olympian who you could add weights to the barbell, you could get stronger, right? It gets bigger, you get stronger. That's your Milo barbell. Also, not coincidentally, my son is named Milo. One of my grandmother's birthdays is coming up. She's going to be 90 in a couple weeks. And so when Valerie was still pregnant with Milo, my grandmother's like, well, what are you going to name him? So I told her, and she's like, oh, that's a really interesting name. Why? And so I explained the story, and I'm all excited, telling her, like, yeah, he threw this ox calf on his shoulder, and he'd walk around. And she was like, oh, that's nice, dear. She was so thoroughly unimpressed with that name. But anyway, I think it's cool, so that's why he's named Milo. But there's that concept of progressive overload, right? All right, so this will be our last thing for today. So if you apply an overload stimulus, you're going to damage the muscle. But within limits, that's what you're looking for, because that's going to cause the muscle to adapt. So delayed onset muscle soreness, the abbreviation is DOMS. So delayed onset muscle soreness is the muscle soreness you get 24 to 48 hours after training. So if you go, let's say, run an 800 or you run a mile, you're going to have some burning in the muscles, and you could describe that as soreness, but that's not what we're talking about. So delayed onset muscle soreness is the kind of soreness, again, that kicks in at 24 to 48 hours later. It's caused by muscle damage. And an important thing to know is it is not caused by lactate or lactic acid. And this is also one of Dr. Kephardt's pet peeves. So if you tell him that soreness is caused from lactic acid, he's going to be mad at you. So muscle soreness, at least delayed soreness, is caused by damage to the muscle. And so what happens? Well, you go lift weights you're not accustomed to lifting, right? So you lift heavier weights, you cause the muscle to generate a lot of tension, you get good interaction of actin and myosin, but by causing the muscle to generate too much tension, you're actually going to damage those contractile proteins. You're going to damage the actin and myosin, you're going to damage or disrupt those sarcomeres. So in terms of what you're looking at here, so all the way over here on the left, this is a single normal sarcomere. So here's your Z line, here's your I band, A band, H band, M line. All right, so, and then here's your other Z line, okay? So that's an individual sarcomere, so that's a healthy sarcomere. Then if we go lift weights, what you'll see, so down here, on all the muscle damage, it kind of looks like somebody just took an eraser to it. And so you can see down here at the bottom in the middle picture that there's somebody, looks like they took an eraser to a couple of the sarcomeres. And so you've disrupted those sarcomeres, you've disrupted that myofibril. That kind of focal muscle damage is going to cause soreness that'll last for probably about 2 to 3 days. So that is, you went and did a bunch of push-ups, chest is kind of sore, your arms are kind of sore, but 3 days later you're good. So that's what you did there. And we'll talk about muscle growth probably on Friday. Then, if you did more than that, so let's say the moderate muscle damage there on the right, so again, just to compare, you can see this sort of little smudge there in the sarcomere down here. And then over here with the more moderate muscle damage, there's a lot of smudging. We got a bigger eraser out, effectively. And so that type of muscle damage there on the right is, you know what, I haven't lifted in 6 months. I'm going to go do like 5 sets of 10 on squat. We'll see how that turns out. I can't walk for a week. That's that. So that's the kind of soreness that lasts for about a week. Now, muscles are different. Like lower body soreness tends to linger a little bit longer than upper body soreness. But in general, so that's the enough damage, extensive enough damage that it lasts for about a week. And then if you're like, I'm going all out, I'm completely detrained, but I'm going to go do frog jumps from one end of the gym to the other for 20 minutes or something crazy, right? Then you get extensive muscle damage. So you can see it doesn't even look like an eraser anymore. You've just like shredded that muscle fiber. And so that type of muscle damage is going to take about 2 to 3 months to recover from. And so that's what you get if you get rhabdomyolysis. So rhabdomyolysis is such extensive damage to the muscle cells that you actually cause white blood cells to come into the area and clean it up. So white blood cells infiltrate, they're going to clean up. We got to get new fibroblasts to lay down collagen in the area. And so that's the type of muscle injury that can put you in the hospital. Because effectively what happens is you do so much damage to so many muscle fibers that their contents leak out into the bloodstream. And so slow twitch fibers in particular have a protein called myoglobin, which is I mentioned on one of the shows, it's the shuttle bus for oxygen from the bloodstream to the mitochondria. And so if myoglobin leaks out in the bloodstream, the kidneys, one of their jobs is to filter your blood. So myoglobin can kind of collect along the tubules of the kidneys and basically obstruct your kidneys and cause you to go into kidney failure. And then you collect too much, you get too much buildup of too much urea, you have problems reabsorbing your electrolytes, can trigger a heart attack, all of those kinds of things, right? So that's really bad. So too much exercise, if you're unaccustomed to it, can kill you because of diffuse damage to the muscle. So that's too much. We don't get beneficial adaptations from that. So like one of the causes of that I've read about in the literature is like people doing, you've seen the CrossFit like kipping pull-ups where people do like 100 of them. There's a really big eccentric component to the biceps for that. So you pull yourself up, but then you're kind of fighting it on the way down. And if you do that 100 times or something consecutively, it's easy to induce that level of damage in the biceps. Also with different like plyometric or jumping kinds of exercises, you can induce that kind of damage. So what ends up happening? All of that stuff. The gist of it is that you cause damage to the muscle cell's membrane, to the sarcolemma. So this is just kind of with a delayed onset muscle soreness. You lifted weights, 2 days later you're sore. What happened? So you damage the muscle cell's membrane, the sarcolemma. And so because of that, it's not as good at keeping those normal electrochemical gradients. It's going to allow calcium to migrate inside of the muscle cell more than normal. And so there's a concept that we'll talk about a lot in ANP2, which is osmosis, which is basically where it's water movement. And so if a bunch of big particles like calcium move inside of a cell, they end up pulling water with them. And so that's going to cause the cell to swell. And so you've probably noticed if you're really sore, like those muscles are swollen for a couple days, right? And so what's happened, again, so that calcium has migrated inside the cell, pulled water with it. When that cell swells, it also pushes on some free nerve endings, right? And those free nerve endings are extra sensitized because of the damage to the cell. You've started an inflammatory process, and some of the inflammatory proteins hypersensitize those free nerve endings. And so now every time you move, it hurts. The muscle cells are swollen, so that causes the free nerve endings, causes pain perception from the free nerve endings. But it also then initiates that rebuilding process. And so we'll activate satellite cells to help rebuild the muscle cell. And so we'll pick up with that on Friday. So we'll talk about building muscle on Friday. All right, so we'll see you then. Again, don't forget to take the quiz at some point tomorrow, and the next time I'll see you will be Friday.